Good morning, good afternoon, or good evening, whatever it may happen for you. Once again, teacher course, and today we are looking at energy stored in a charged capacitor. We have seen the charging process of the capacitor, and then today we want to look at the energy that is stored by that capacitor. We are going to actually find out that the energy charge stored by a charged capacitor is equivalent to work done in moving the charges from one of the capacitor plates to the other through, of course, an external circuit. Because how does it happen? A capacitor, let's say that these are the plates of the capacitor, like any neutral atom. There is always a positive attached to a negative charge. Okay? Just to know if it is a neutral atom, that is how it is. And the same thing this side. Each positive with a negative charge. So our role is to make sure that we separate, so that maybe on this capacitor plate we remain with only positives, and then on this we remain with only negatives. I'm saying we want to take away this positive charge, so that when this positive charge comes here on that negative charge, what happens? Now this positive charge will neutralize this negative charge. So what do we get? We shall only find that this negative charge is not there and this positive charge is not there, and therefore we have a negative charge and a positive charge, and therefore we are already setting up a potential difference between the two plates, and therefore we have started the process of charging the capacitor. We are doing this one through the external circuit. Okay, but I'm giving you a clear scenario. We are doing it through the external circuit, maybe by connecting this one to a PD source. Okay, so if you connected like that, then of course remember we said in our previous lesson that when this switch is closed, then we shall have the negative charges move from this terminal, and then when they come, of course, they will be neutralizing these positives one. Okay, and as they neutralize the positive ones, also now so meaning here you are only remaining with the positives. Then we shall also be expecting, because as they neutralize, the PD here is reducing. So we shall expect also these negative ones. Okay, they will also have to flow. The negatives will also flow and occupy this terminal. Is that one clear? And therefore, here we remain with negative charges, and here we remain with positive charges, thereby charging the capacitor, thereby setting up a PD, thereby giving it a charge Q. Right? So this is the process. I want us to go step by step. How do we get the energy? We are saying that the energy is work done. The energy will be the work done. So the energy to have one electron pile up here is the work done in making that one electron pile on that plate. What am I meaning? I want you to look at this. This is the plate of the capacitor. So for us to have this first one, to have, let's say, I'm just taking this scenario. For us to have this come to this, it would require almost no energy. Okay? So for us now, for us to have that one, that means this will become positive and this will become negative. So for us to have that one, it almost requires no potential. It requires so little energy. So we can almost say the potential required to do that, because the work done is V times Q. But then, of course, that one will be the Q. But the V required will almost be negligible. So it will be 0 times the Q. Let's look at the second one. So if I'm to have the second one, this one, neutralize this. If I'm to have the second one, neutralize that. Already, this one is already positive. So to have another positive charge there, it will be repelled. So you need more of the potential to do that. So some kind of potential, but small. Then times the Q. The Q is the same. To have the third one, now it would need now a bigger potential than the first, than the second, but slightly bigger. So that would be some V. I'm increasing on the side, the Q. To have the first one would need more, the fifth more, and then to have the very last one, so that the potential across this now will be equivalent to the potential across this. To have the very last one, the very last electron piling there, here at the Saturn, okay? Now we have the very last one. We have this one. Move from here to this side. Oh my goodness. It would need more potential that is almost equivalent to this one. It would need more potential to drive it. And therefore, we would have that kind of V, then times the Q. That would be the total work done to have this capacitor charged. And therefore, mathematically, we are going to have that this one would be the integral. Okay? So the work done, the total work done, would be the integral from the charge Q is 0 at the beginning. This is not charge. This is at 0 charge. And then to a charge, the maximum Q of V, then the Q. That is the mathematics that brings how beautiful it is. And therefore, the work done. We know that capacitance is Q out of V from the definition. Therefore, the V will be Q out of C. Therefore, V will be Q out of C. Okay, this is what will be your kind of side one. So when we substitute it here, we shall have Q out of C, then the bro, then Q. The capacitance is a constant. Therefore, we can bring it outside, 1 over that. Then we are integrating Q, then with respect to Q. When you integrate, you increase the power by 1 and divide by the new power. So this becomes 1 out of C, then the Q squared out of 2. Then we are putting our limits from 0 up to Q. And when you put the limits, you are going to substitute this one on top, which you call the upper limit here. Then you subtract when you substitute this one, and that one will become 1 out of C into Q squared out of 2 minus 0 squared out of 2, and which turn out to be 1 out of C into, this is 0, so this is Q squared out of 2. That is the work done. But remember, we are looking for energy, which we said is the work done. I guess you captured this one very well, so I could get it off. So therefore, the energy stored in a charged capacitor is equal to Q squared out of C. That is the energy stored in a charged capacitor. Meaning, when I have the capacitance of the capacitor and then I have the charge stored, then I can get the total energy stored in a charged capacitor. That is it. Then, what if I don't have one of such parameters? Maybe I have the capacitance and the voltage. How do I do that? Remember, from Q, from capacitance is Q out of V. You can make Q the subject, which would be CV. So Q would be CV. Substitute it here. So the energy would become, Q is CV, so this will be C squared, V squared out of 2C. And this would become, the C would cancel with C, remain as 1C, so it would be 1/2, then CV squared. So that is another expression for energy. Therefore, energy would be 1/2 then CV squared. So if you are given the capacitance and the voltage, you can also be able to get the energy that is stored in by that kind of capacitor. Then, what if now you have the charge and the voltage? You don't have the capacitance, you have the charge and the voltage. Here there is no charge and voltage, it's still charge and capacitance. Here is capacitance and voltage. So we can have charge and what? So we need to eliminate the capacitance. So from the definition that we also have, we can also say that this energy can now become 1/2. Capacitance is Q out of V. Q out of V, then times V squared. So the V will cancel. Okay? The V will cancel. So it shall remain with Q V out of 2. So energy will be QV out of 2. So that is another expression for the energy that is stored by a charged capacitor. That is teacher course at Baxter's Education Consultants, and this energy stored by a charged capacitor can be obtained in different ways. Some use curricular, some use graphical. So feel free to interact with the internet and you get anything as you supplement on this. But I keep encouraging you. In the next video, we are doing numerical calculations about this, that the energy stored is Q squared out of 2C. We just have to get that one off head, that the energy squared is 1/2 CV squared. Get it off head, and the energy is 1/2 QV. You also have to get it off head. Thank you for watching.